Hi, finally I'm back. I had some things to do, but now I have some more time to produce videos. So I wanted to show you how you can use Rust to program microcontrollers and build your own audio hardware. Rust runs perfectly fine on a lot of different development boards already. Like, I don't know, what do I have here? Some Raspberry Pi, Pico. What do we have? ESP as perceived development boards, basically everything where an STM runs on there, like Cortex M chips. But if you want to do audio development, a very nice platform is the Electrosmith Daisy Seed. And the Daisy Seed, you see, it costs only $20, has a lot of RAM, a quite powerful processor with 480 megahertz Cortex M7 with floating point support, hardware floating point. And the platform is kind of nice because you find those Eurorack modules that you can just use, or you can buy this pod, which has already audio I/O with those little jacks here. And this is what we have here. Yeah? I'm already connected this just via USB. And you find some stuff like an encoder, a POTIs here, 2 buttons, LEDs, stuff like this. Yeah, a headphone output, line in, line out. It's a quite cool platform to get started to experiment a bit with audio on hardware. But yeah, also those other devices here should work fine to do it. But the basics you can just do with a $20 Daisy Seed. How can we program this thing? Yeah, you will find some help, for example, here in this Getting Started guide, here daisy.audio tutorials. This is mostly for the C++ setup, but if you have some problems following along, you can always look here again how you can flash the device and some stuff like this. All right. The cool thing is that, so to build for a microcontroller, first you need the toolchain. And Rust, the toolchain is already officially available. But on top, you need some access to the CPU. So you need a crate that gives you access to the functions of the microcontroller. And on top, specifically for the development board. So for example, that we can directly access the audio from the codec. And someone luckily already did this. This is a ZLO synth, like a Eurorack developer. And this person has published a hardware abstraction layer for the DAISY boards. And supported I think those are all versions of the Daisy Seed that ever came out. They switched in between sometimes the codecs because of chip shortage. I here have the WM codec, which you can find if you look on the board itself. Then you see this is the STM microcontroller. Here is the memory, and the last thing here at the bottom is the codec itself, yeah, and on the codec I see already it's the WM8731. All right, there are nice examples for a lot of things like audio input output. Arctic is just a version that is using an Arctic as a real-time operating system, yeah, and this makes very small projects more complicated, but it helps large projects to have kind of multiple processes running that you can synchronize in a way. Even an example for the OLED display that is, I think, here in this Daisy patch, for example, there's this OLED. Yeah, so you find a lot of different nice examples, but we will start with the Blinky one. Blinky is just, we can blink the LED that is here on the board. What else do we need? I made a little Daisy kickstart. Here you find It's public, you can just access this. And you will see here what you need to do to set up. So I'm not 100% sure what you have to do on Windows and Mac OS, but on Linux you have to install some packages. The Probe RS, you have to install this everywhere. Probe RS is just is this project in Rust to use debugger. Yeah, this is an ST-Link Mini V3, a debugger. This is recommended. It's just nicer to program the daisy seed with it and get logs and also put breakpoints into the code. Yeah, that's kind of cool that you can use this. But it also works just with USB, at least the basic functionality. Yeah, follow this guide, how to install it. And then you also need to, on Linux, you need to add udef rules, which allows the system to access the device via USB. So you need to download the rules file and put it here and then call those commands, yeah. And also, yeah, you have to add this here. This is for the daisy seed. Yeah, it's just this udef rule. On Linux, you have to do this, otherwise it won't work. Yeah, if you followed this stuff, we can create a new project. Yeah, maybe I will just, let's see, we'll just open something. Cargo new daisy example. And let's see what we have to add. We need a lot of dependencies actually to properly work with the microcontroller. Let's look into here. Here you see in the cargo.toml file that I added a lot of dependencies. We won't need all of them for just getting started, but you should maybe just copy this, add it here, and see what we have. Cortex M is just the interface, or it's just giving us the functions of the Cortex M chip directly to run, for example, assembly on there or get some timers, stuff like this. The RT is the runtime environment, so for starting up the program. RTIC is the real-time operating system. We don't need this now, we can delete it. DAISY is then gives us access to the audio driver, to the codec, and to some. It just is a wrapper around the functions of the Cortex M, for example, so we can get access to the GPIO and so on. DFMT is for logging. DFMT RTT is the transport layer to send the logs over so we can read them. Heapless and micromath, you won't need it now. It's just when you want to do some, it's nice for writing code. Panic probe is then the panic handler. So if you have a panic or an assertion, the output will send over DFMT. And then we have this STM32 hardware abstraction layer. Yeah, SysTick, we also don't need this right now. This is all you need. Yeah, you don't need the logging stuff, but it's nice to have now for development. Then the next thing we need is this memory.x file. And the memory.x is just for the linker. So it knows where to put which section of the program in which memory and the addresses of each memory. This data is provided by the board manufacturer usually. Yeah, so here's from Electrosmith, but you find it in my Daisy Kickstart here, or also just in the Daisy here in this hardware abstraction layer. Here's the memory.x file. Yeah. What is in there? Let's have a look. It just tells all the memory areas that are available on the board. So we see here 8 megabytes of QSPI, 64 megabytes of SD-RAM, 128 kilobytes of flash, and 512 kilobytes of SRAM. Those are the sections you should know. And then it tells here basically where to put what of the program. Cool. And this is, I think, all we need here from the setup. What we can add to make it a bit simpler is just this .cargo config.toml file, where we say the default target we compile to should be, I think I wrote it wrong. Let's look in here, build, yeah. The target should be this. This is just the architecture, yeah, the target triplet for the Cortex M7. This is thumb v7em non-EABI hardware float. You can also use this and it works, but if you want hardware float support, use this target. Yeah, and then we can go to the main RS. Yeah, this won't work now if you try to compile this, because we still have the standard library integrated now. And the standard library doesn't work on the microcontroller. So here, yeah, we get a lot of errors, cannot find crate for standard and so on. Yeah. Also, what you have to do when you compile for the first time is rust up target add to add the specific target. We already have this. Yeah, so what do we have to do? Basically here you can copy the example code. Let's start with the Blinky example. That's the easiest. And just copy this code. Oops. Let's see what we have here. Because in the DAISY library, you can enable the DFMT feature. This stuff is here, but we don't want to use this right now, so we can just remove this. We want to use DFMT. So let's just leave this line here inside. And now you see no main. That means we don't use the Rust runtime to start the program. We want to use the entry point here from Cortex MRT. We don't use the standard library. And then we want to use DFMT RTT as the transport protocol for the logs and the panic probe as the panic handler, basically. Yeah. The other thing that happens now in our program is just we get the DAISY peripherals, or I have no idea how to say this word, to be honest, the DAISY board. And here we can then get access to the clocks, to the pins, so the GPIO and so on. And then we just say, okay, here we get access to the user LED. That's the LED here on the board. And now, what is this doing? Yeah, we get the system clock in hertz. This is our 480 megahertz, so the clock speed of the processor. And because we have 480 million ticks or cycles of the CPU per second, we know 1 second is 480 million cycles long. So here we run a loop that goes forever, toggle the LED on, off, and then we wait 480 million cycles. That's basically what we do. And you see the delay is coming from Cortex M directly. The user LED and so on is coming from the DAISY crate. Now let's try to build this. Yeah, let's see if that works. Great. Now our program can compile. But how can we now flash this on the device? We have to run a command that is a bit more complicated if we don't want to use the debugger. Yeah, with the debugger here, we can use probe RS. First, we will look into how that works without the debugger. The command is a bit hidden in the library, but you can find it when you go to, let me see, to the make file. There the command is inside. And this is basically it. Yeah? We have cargo, opsh copy, release, example. No example, we don't need this. Let's maybe copy this command. Cargo, and we can remove features. We don't need features, and also we can remove the example part. So this is the command now to build the binary and then create this .bin file, which is what we copy on the actual platform here. It might be that you still have to install opscopy. Yeah, you can have a look, cargo opscopy. It's here part of cargo bin utils, and this is how you install it. So now we run the release build of our program, and this should generate in the target folder program.bin. So this is the actual file that we flash now on the device. And the flashing works with dfu-util. This is just a program to flash things. Let's check again the command here. So this is now specific to the memory region where we want to flash this on. So here you see 0x, 08, and then a lot of, oh, was this right? No. So 0x, 08. And if you look into our memory region, you will find this is the address of the flash. Yeah. So here we just specify the flash address, then we specify the program we want to flash. And afterwards, this 0483 df11 is then the device, the device key. If you remember when we set the DFU rules in Linux, let me have a look. Daisy kickstart, readme. I think here 0483. This is the vendor of the device, and df11 is the product ID. Yeah. Let's run this and see what happens. First, you have to set the Daisy seed into a state where it can accept new programs. So we press the upper or righter button here. That is the boot button. And then while pressing this, we press the reset button. And now the board is in the reset state where it can accept new programs. So if everything is configured right now and you have the UDEF rules set right and so on, you can run this command. And it doesn't work. That's great. I forgot to put in something here in the config file. Let us see what I forgot. Daisy kickstart, config.toml. I think those linker flags are missing. Let us try again. Cargo opscopy. And yes, now it's working. And you see the LED is blinking. Perfect. So that worked already. Yeah. What was missing here is this t-link.x. This is just an argument, so it actually uses the memory regions correctly. Okay, now we can modify it. Yeah, for example, instead of 1 second, we could use 2 seconds. Let's try this. Cargo opscopy, and then reset the board again and call dfu-util. And now it's downloading the program, and you see the LED is blinking with half the speed. So that works great. Yeah? Now you know how to flash the board. And the last thing I want to show you is how to use the debug probe. You just put this cable that comes with it onto those pins so that it's exactly centered. So the space here and here is similar. And now we can flash the board with an easier command without pressing anything here. Let us try this. Yeah. Now the command that we want to run is probe rs run, with the right chip. And now the cool thing is we can just say cargo run release. Let us test this. And you see, perfect. Erasing, programming, finished, and the program is running. And let's do a change just to verify that we really run a different program. Maybe we can try double speed, yeah, half a second, cargo run release. And now the LED is blinking with twice the speed. And what we can do as well now is seeing logs, dfmt, print line, hello Daisy. Let us try this, cargo run release. Hello Daisy. Perfect. We see the output of the device in real time. And I think this, just with this cargo run release command, flash everything, do everything, is so simple and so much nicer to develop than a lot of stuff I used before with C and C++. But yeah, it mainly comes to the tooling again, right? Because the tooling is so nice. And if you want to access the audio, let's just have a look at the audio example, because it's also quite simple. Copy the file. You see there is a little bit more code, but what we have here is the audio interface. We just store it in a global mutex. So we have a mutable global location. This mutex here now is not a system mutex like on your desktop. It's a Cortex M interrupt. So it's actually real-time safe. Yeah, everything you do on a microcontroller is basically real-time safe, other than sleeping. So the mutex here works different than on your desktop. So it's fine to use. Now we can enable those caches. This just is improving the performance on the device. And then here with this board split audio, you get the audio interface. We spawn the audio interface, put it into our global variable. And then we just blink so we know the thing does something, it's working. And all the rest is now happening in this interrupt. Yeah, DMA1 STR1. This is just the stream of this DMA. And inside of this interrupt, yeah, we get our audio interface, we borrow a mutable, and then we handle this stream, which gives us the audio buffer. And the audio buffer is always the same block length. Yeah, the block length is configured at compile time. You can change this with the Daisy features, and it's always in 48 kilohertz. And you can also set the device to run in 96 kilohertz with a feature here on the Daisy in the Daisy crate. Yeah, you can set here a different block length at a different sample rate. But this will now be always the same with the left and the right sample in frames. So here we iterate through the frames and then just change the level. And this should work. And then you just hear the audio output from the audio input that you put into here. Yeah, this is just a small getting started, knowing what you need. Test it out. Yeah, it's very nice to program like this. Really, I recommend getting this debugger. It's just nicer to code like this. And yeah, next time we will look how to build a filter into this device now and actually change the parameters of the filter with those POTIs. I hope you stick around and see you next time. Bye bye.